Ready to party?
Yes, sir.
Now you're really ready? Oh yeah? La vida loca? All right, so today we're going to get into the advanced DMM, some of which you did already, but I'm going to bet you're not able to apply it. So we're going to go from where you guys could follow the worksheet and measure, for example, frequency and be like, yeah, I can measure frequency, to how and why and what would you do with the measurements to be able to tell the customer what they need to know. You need to be able to recommend a part that's going to fix the problem, you understand? So the customer never comes in and says, will you please measure the duty cycle of my EGR valve? They're never going to say that. What they're going to say is, my check engine light's on. What they're going to say is, when I turn my AC on, it blows warm. And what you may have to interpret is, well, when I turn on the blower speed for the interior, the blower motor, the blower fan, it doesn't work. If it doesn't work, what do we need to replace? Maybe it's the motor. Maybe it's the harness. Maybe it's the ECU. Maybe it's the control panel, right? So if you can get to the point where you can take the customer's car that's broken, determine what the actual problem is, diagnose what the problem is, and convert that into what part are they going to need, then you can make some money. So you guys back there, you're ready to do it. You talk a lot in the back row, don't you? Brandon, settle down. All right. If you want him to teach the class, he could teach the class. Come on up. Oh, no. All right. So then chill out back there. All right. So if the customer comes in, like I was at a dealership last night at 4:45, and they had a vehicle that the rear lift gate wouldn't close. And, well, it was intermittent, though. So sometimes it would work, and they tried it 10 times during the day. The tech got ready to leave, went to go close the lift gate, and it wouldn't close. It opens, it goes brrr, and then you go to close it, and it just beeps at you. And then it's like, what do I do? So you have to know what part you're going to sell or what thing you're going to repair. Make sense? That's the difference between like class and school. In class, it's sort of like, you guys are going to measure this thing today. But when the customer comes in, they don't tell you to measure anything. They just tell you my lift gate won't close. My blower doesn't work. In fact, they probably won't even tell you my blower doesn't work. They're just going to tell you the AC blows warm. So sometimes it's simple. You're checking for 12 volts. You're checking for ground. Other times it's a little more complex. You may be measuring AC voltage. You may be measuring frequency, right? It might be PWM. Anybody know what that is? PWM. You started. Come on. Pulse width modulation. So it was close. So if you look at the on time has a width in milliseconds, right? So, or what if it's duty cycle? Duty cycle has nothing to do with the restroom. The duty cycle is a percentage of on and off, right? So there's these weird things that we showed you how to measure, but then you're kind of like, all right, yeah, I can measure duty cycle, but why would I measure duty cycle? Well, if we jump back to that customer came in with my AC blows warm, you jump in the car, you turn the blower up on high, the blower doesn't work, then you're like, maybe it needs a blower motor, but you don't know that. You could throw a blower motor at it, and if it fixes it, you're the hero. And in the somewhat likely case that it doesn't fix it, then you're like, I don't know, I'm not a mechanic, and then you have somebody else look at it. Or you say like, oh, we need to get the foreman. And, and when you're new, that's okay, but these are things that you want to be able to diagnose. If you kick every hard job to the foreman, you're just entry level. Then of course you'd be like, hey, I want more money, and they're going to say like, if you want more money, you got to be able to do more high-skill jobs. You guys know that, right? That's just the way that the market works. Cool. So we'll get you that level, and then, and that's, to be honest, this top half is my go-to. If I can diagnose the car using the meter, that's my go-to. If I can't, and I have to get a DSO, which is just digital storage oscilloscope, we're mostly going to cover Picoscope. I'll get the Picoscope out, like Eloy was just telling you. Today you guys are going to get the Picoscope out and look at some things. I will if I have to, and sometimes I have to, but I don't do that first, though. If I can get it diagnosed without it, I'll shy away from the Picoscope just because it's just more time. You know, you get the computer out, you get the program booted up, you got to get your leads in, you got to, you know, set your different readings on the Pico program. There's a little trick. Sometimes you can hit the lightning bolt and it'll automatically do it. So in that case, that's kind of nice. But it just takes a little bit more time, and time is money. You know that, right? And so if you want to actually see the waveform on a graph, the meter doesn't do that. So the meter gets you so far. And then if you need more, you're going to need to scope it. So Picoscope in this example. Cool. And Pico, I'll explain real quick the reason that I'm gonna mostly stick with Pico. A DSO could look kind of like this meter right here. It could be like you know, your basic handheld fluke thing, but it'll have a bigger screen, and you could make your connections, and you could set all your functions manually, and you know, set your milliseconds and set your voltage, and then you can get the same waveform on a DSO, like a fluke, or Altel makes them. There's Snap-on makes scopes. You can get all that. However, this meter is probably 10 years old. Anybody got a 10-year-old laptop? What the heck are you going to do with that? Have it hold down papers on the desk? You know, like the scopes are the same. So the actual self-contained DSO oscilloscope has its own processor, its own screen, its own stuff. Then 10 years later, it's like, whoa, that thing is way outdated and it's not fast enough, it's not that good. So let me explain what Pico is. Picoscope, that little box, all it really is, that's just a signal converter. And then you know what does the processing? What has the processing speed with Picoscope? Whatever laptop you got it plugged into. So if you get a new laptop that's got 16 gigs of RAM, now your Pico's got 16 gigs of RAM. But if it was 10 years ago and you had 4 gigs of RAM, your Pico's got 4 gigs of RAM, right? So to me, it makes a lot more sense when you get the Pico, which is really just the box and the leads, and it works with your existing PC, and every time you get a new PC, you get a faster and faster oscilloscope. So that's the go-to. And at the end, I'm going to show you the Pico website, and they're compiling waveforms and guided tests, and Pico's just really the way to go. Technically, the ASE will never call out Picoscope. You know why? It's a brand name. They can't be like, you can't have an accrediting body listing a brand and saying the Picoscope, because somebody may be like, I don't use Pico, I use the Snap-on scope, and I'm upset. So they're just going to say DSO. DSO just means generally oscilloscope, right? All right, good. So from there, let's say we're going to go and just review the meter a little. Normally, you're measuring voltage. You might measure amperage. You might measure resistance. And we still do that. And that's very normal, and that's probably the majority of the time. But if you need to do a little bit more, we can still use the meter for that, such as the frequency, the duty cycle. You can record min-max. You guys got a little experience with that. That was good. But we'll link it to really why. But let's just say if you're going to measure frequency, you can get a number. 60 hertz, for example. If it's supposed to have 60 hertz and the meter tells you it has 60 hertz, you're like, yeah, it's good. But once in a while, you'll get a problem where it's like, I still can't figure it out. Like, I've done some measurements, everything checks out, and yet it's still having this malfunction. So like the best example I can give you is a wheel speed sensor. So if you have a wheel speed sensor that's measuring the speed of your wheel, as you're driving, you know, it's an input for ABS, a lot of times an input for the transmission, for your speedometer and everything. So if your wheel speed sensors, you know, got a code or it's not giving you the right speed or something, you can go ahead and you can measure for ASE frequency. It's actually how the older sensors work. They change a little bit. You could measure it and be like, yeah, this is giving me a reading, like it's good. But that sensor reads a spinning wheel called a reluctor, and if it's got one damaged tooth on it, it'll actually give you a good number on your meter, but the computer will actually sense that there's a fault. Make sense? Or it'll at least get a signal that's wrong. So you'd be like, how do I really diagnose this thing? I've checked what I could check with my meter. You might have to go outside the box and be like, you know what, let me shine a flashlight on this problem so I can actually find the defect. Well, that would be this screen right here. So we went ahead and we hooked this up to an oscilloscope, and we set our time divisions, and we set our voltages, and we set it to AC. And what a frequency is, it's one cycle. So if you go from red line to red line, it's just telling you that's how frequently it goes from, let's say, positive to positive, or from negative to negative. It's how frequently it's gone back and forth in a set amount of time, right? So 60 hertz is giving you a specific 60 times per second it's cycled from positive back to positive again. Or from, in this case, we're kind of reading on the downslope to the downslope. If it did that 60 times in 1 second, you would therefore get your 60 hertz. Your meter will spit out 60 hertz, and you'd be like, it's good. But then if we put the oscilloscope on it, what if we had a damaged tooth? What do you think this might look like?
It has like a gap somewhere.
Yeah, that's exactly it. So I'm going to, the truth is I messed up one time when I was an apprentice, and I drilled, I don't think I told you the story, so I'm going to shorten it. But I drilled, I was supposed to file out an ABS sensor bore in a wheel bearing. And, you know, you can file it like this, like really carefully. And then I was like, you know what? I'm going to use a drill bit on a drill. And it was really fast. And I really went a little too far, and I drilled off the top of one of these teeth. And I kind of thought I felt something, but I was like, it'll be all right. And then shipped the car, and the customer went to hit the brakes. Well, actually, I didn't get it to the customer, thankfully, but my mentor went to drive it, and he went to hit the brakes, and the ABS activated, and it was like, why did the ABS go off? And it kept doing it, and it was like, there's something wrong. So he measured a bunch of things with the meter and measured this and checked that, and he's like, did anything go wrong in that job? What did I tell him?
No, I didn't.
No, it was fine. And I probably should have said, well, I didn't do what you said. I used a drill, and I think I might have went a little too far down, but I didn't tell him that. Because it was like, I don't know. It's kind of like if you're scared of something and you do this, you feel better. The thing is still there. So I kind of knew, but I let him try to figure it out. He went and ended up having to go get the oscilloscope, and he graphed it, and one of those peaks looked like a drill bit hit it. And he looked at me and he was like, did you use a drill bit? And I was like, yeah. And he's like, I'm not even that mad you did that, but why didn't you tell me that like an hour and a half ago? I've been goofing around with this job. Like, remember, technicians flat rate pay. So he wasted an hour and a half. I could just told him, hey, I think I sent the drill bit a little deep. You know, and then he'd be like, look down with a flashlight and be like, oh yeah, the tooth is damaged. You know, but I've sent him on this wild goose chase. Is it a connection? Is it a module? Is it a bearing? Is it a whatever? No, I sent the drill bit in too far, right? So when we say, you know, get the Picoscope or the oscilloscope out, that's going to really show you what's up. That oscilloscope tattled on me so bad, and I had to own it at that point. See, I thought it was going to be a mystery forever. I thought I could be like, I don't know, maybe try changing the whole assembly and that'll fix it, because that'll actually fix what I did, but he won't figure out that I caused it. You know, I was hopeful. I wasn't real honest at the time. All right, so this is an example of an ASE waveform. And honestly, we could get that measurement on the meter, but guess what? The meter shows you your whatever, 60 hertz or something, and you think it's cool, but if there's one damaged tooth, the oscilloscope will tell you everything. Like, let's say you have a spinning, imagine a sprocket, right? Like a gear, like a sprocket off the back of a bicycle. We have a sensor that's going to look at each of those teeth and essentially measure how quickly they go by, how many go by, and that can determine speed. What if one of those teeth got like bent or like broke off or something? Exactly. It'll mess the signal up. So while we use our meter, the meter is going to sort of average our measurements and spit out a number. It's very helpful. The computer is actually really looking at that waveform and interpreting that information and converting it to a speed or to an RPM, like a crankshaft position. The crankshaft position measures the teeth as they go by to tell you exactly where the crankshaft is to prepare for firing the spark plug, you know, on just before top dead center compression, right? So like the computer needs good information, not like missing a tooth is damaged. It can't have that info. And if there's a defect, either A, the computer will set a code, and then you're diagnosing it for the DTC-based diagnosis. Or B, it won't set a code, but it'll have something. Like maybe it stumbles if it's a crankshaft position sensor. Maybe if it's that wheel speed sensor, the ABS goes off. Maybe if it's a transmission output shaft speed and the tooth is damaged, your speedometer may go, if you're doing 60, all of a sudden it may say 50, 60, 50s. It'll do something weird. So the way that we do school is a little backwards because it has to be, because we know what you need to know. So we a lot of times start with what you need to know and miss the fact that why do you need to know it? So I'm telling you, if the car comes in and it's got a speed sensor related issue, you can do a bunch of tests, you can measure a bunch of things, but at the end of the day, you may have to employ the Pico or the oscilloscope to really evaluate it and then be like, you don't need a new sensor, you actually need that sprocket that's got the broken tooth. But how did I know that? Because I used the Pico and I could visually see it and I can prove that it's bad. And then the customer's like, well, why didn't you just sell me the sprocket in the first place? Like, man, I didn't know what was wrong. It could be the sensor, it could be the wiring, it could be the module, it could be the sprocket, it could be something else. Sometimes that sprocket sits on a bearing, and if the bearing is loose, the sprocket will go out of the sensor's window, if it's loose. So it's we don't, truthfully, when the customer comes in with a concern, we don't have any idea what to sell them. Honestly, we don't. And that's why they sign for diagnosis time. And if you get an hour diagnosis time, you can burn through that hour really quick. So sometimes, you got to put in a little extra time. So that lift gate last night at 4:30, I have no idea what the fix is for that car. I teach the class. I roll in, the lift gate won't work. They're like, hey, what do you think? I'm like, not the slightest clue. No idea at all. Going to have to read about it. Going to have to consider what tests. And the tech checked, and there was a lost communication with the rear liftgate ECU. So if you remember what we covered last time, that'd be like, oh, the computer's offline. Why is it offline? Is it getting voltage? Is it getting ground? Is it connected to the network? That's how you really, truly diagnose. You don't just be like, oh yeah, it's got a bad ECU. How'd you come up with that? So it's pretty easy for me to probe whether or not somebody's being honest, to be like, yep, I checked it out. It's got a bad, whatever, wheel speed sensor. Oh yeah, cool. What test did you do? Well, I checked it out. I'd be like, oh yeah, okay. What were the readings? It was bad. It was bad, was it? And so, and the people that you're going to try to get paid from, probably a warranty administrator or Honda corporate or another manufacturer, they know. They see technician stories. So when you can't write a good story as to how you diagnosed it, they're probably not going to want to pay you the diagnosis time. Then you'd be like, they don't pay me to diagnose. And it's kind of be like, well, they read your story and it's very clear you don't diagnose. You just shoot some stuff at there, and eventually if you change everything, it'll probably fix it. All right, so this would be a DC though. You see the difference? AC. AC is mountains and valleys. DC is the city skyline, square wave. Cool, that's the main difference. If you try to measure an AC sensor with your meter on DC or your oscilloscope on DC, you're not going to get anything that's logical. You're going to get some weird squiggles, nothing. And the other way around. So you got to know if the sensor is going to be AC or DC. And then towards the end, I'm going to show you when you'd employ these tests and how you'd know what to set it up, your settings at. All right, cool. So frequency was pretty easy. I'll jump through a couple of these, and I want to change over to the camera so you can actually see. We were talking about 60 hertz. I'm going to call that 60 hertz. That's 59.98. That's 60 hertz, right? We joked around about when we get a brownout power outage, when everybody turns their AC on. When everybody turns their AC on, there's a lot of demand. That big generator, which I'm sure is fueled by something really environmentally friendly. That big old generator burning some sort of a fuel that we won't even imagine it'll bog it out. It's sort of like if you put too much load on your engine, you know how the RPMs drop? It'll actually bog that generator out. It'll slow down. You know what that'll do to our frequency? It'll slow the frequency down. It'll lower the frequency. So 59.98 is great, but if you start to get 50 hertz, that's when you're going to start to get your lights are going to start to go like a little more orange, a little more brown. It's a brownout. You're overloading the grid. That generator cannot keep up. Makes sense? So this would be a down and dirty way to get an idea what's going on with the power grid. Just measure how many hertz it's at. And if you start to see it dropping down, you're like, uh-oh, we're overloading it. Makes sense? Cool. And so we do measure frequency on the car too. And what are we doing really? We're comparing with the given specification. So over and over, this is going to be the key. You're going to take a measurement and you're going to compare it to a spec. I happen to know the spec for what comes out of the wall because 60 hertz is standard for North America. But if it's on a car and I'm trying to measure a speed sensor, it's going to probably give me like somewhat of a spec, but it's going to depend on the speed of the thing, the wheel, the crankshaft, the transmission output shaft, the whatever. Not just take a measurement, like put a number on a sheet, like a worksheet. School's critical, but I like to try to link it back to why you're doing it, right? So you'd be like, hey, what's the hertz? What's the frequency on this speed sensor? And you're like, 59.98. Move on. But is that good or bad? I don't know. What do I need? I need the spec. If I don't have the spec, I don't know whether that test was a pass or fail. Make sense? That's kind of what this is saying. And duty cycle is another thing. So this is going to be what the measurements are, and then I'm going to show you how to do the measurements, which you have done, but I think they'll make more sense now. The duty cycle, if you look at it, it's on and off time. So if you look at this right here, and you were to measure that, you'd say, it's on for 2 squares, right? How long is it off?
2 squares. 2,
and then it's back on, then it's back off. So if you compare the on to the off, what percentage would you say? 50%. That's a 50% duty cycle. Yeah, it's half on, half off. Make sense? That's literally what duty cycle is. So if I use my meter spits out a 50. I'm like, okay, 50% duty cycle. Cool. If you use an oscilloscope, you see a waveform like this. And then you're going to be like, oh, what is that? Yeah, they're about the same. You can do some measurements. You can, on Pico, you can actually use a little measuring tool to measure the on and off time. And if it's the same, if let's just say they call this, that's actually going to be 1 second of on, or let's say milliseconds in this case. If it's 1 millisecond on and 1 millisecond off, those are the same. That's 50% duty cycle. What if we decide we go in the car and we want a little bit higher fan speed? That computer is going to send a different signal to have the fan turn faster. If you want the fan turn faster, you think you want it on longer or off longer? On longer. So what if we bump it up to 75? Look right here in the middle, that's 75% duty cycle. You got 3 squares on and then just a small amount of off time. 3 on, 1 off. 3-to-1 ratio, like I would change it over to quarters. If you got 3 quarters, but not the 4th quarter, that's like 75 cents. That's 75%. Right? So when we built the system, on 100%, that's just like $1. So I'll always resort back to the dollar. I can't really use minutes because we did it at 60 seconds and 60 minutes, and I wasn't there for that decision. So I would like it to be on hundreds if you ask me, actually. Don't know how to do that. Right? So that's 75 on, 25 off. Now, why would we do this? Well, if we go to turn the blower on and the blower speed doesn't seem to match what we want, maybe it doesn't work at all, we actually have to know what is the computer sending down to the blower. If I've got it on the midway point, what do you expect to see for duty cycle?
50.
About 50. So I could go right down there with my meter and be like, is this getting 50% duty cycle? No, it's getting 0. And I'm like, what? The blower's not bad. The computer is sending 0% duty cycle. I got to look up in the computer area. Or maybe the computer is sending 50, but the wire's broken. So what's the blower motor get? 0. See what I'm saying? It's kind of the same as how you check voltage, but you're going to have your meter set to duty cycle. And you're going to see what's coming out of the ECU and what's making it to the motor. And if it's got 50 coming out and 0 making it, you're like, there's a break in the wire. Then if you really wanted, you could eliminate the duty cycle thing and just measure the resistance of the wire, and you'll find, what would you find if it was open?
Overload.
OL, yeah. So you'd be like, OL, all right, cool, it's a wire. So should I sell the customer a computer and a motor? No. Find the problem with the wire, right? So that's really why we do what we do. Cool. And then, of course, you can have a 25% duty cycle. That'd be a quarter on and 3/4 off, right? So it's not really that complex. All right, and then sometimes when we talk about min-max, just to apply it, all it's going to do is record what the minimum was and what the maximum was. The reason you want to know that, sometimes we deal with intermittence, just like that lift gate that wouldn't close. He tested it all day long, just kept testing. It works. And I'm like, I don't know, maybe this customer's lying. Maybe they paid too much. It was a brand new Sequoia. It was really nice. Those are actually pretty. This was like top of the line Sequoia. Maybe their payment's too high. Maybe they realize they shouldn't have bought it. Maybe they want it back. You start to think these things. But then, sure enough, boom, the thing doesn't work. And you're like, all right, cool. Now I know why it's in the service department. All they really want is their power lift gate to actually close when it's supposed to close. Make sense? Now we need to fix it. But if it worked all day and now it doesn't work, you can understand it could happen on a faster scale too. Some could work, not work. So how would you catch that millisecond that it didn't work? Probably min-max. You might be taking a measurement and being like, it's got 12.6 volts, but set min-max and keep trying it, and all of a sudden you might notice the minimum was 0.0 volts. So at one point it lost voltage. Why did it lose voltage? I don't know. I would keep it on min-max. I would keep it probed, and you know what I do after that? This is very technical. I do the wiggle test. You know about the wiggle test? I'm going to put on min-max, and I'm going to start wiggling the harness. You think I'm kidding. I'm dead serious. And if I wiggle the harness right here and no change, I wiggle it right here and no change, then I wiggle it right here, and it drops to 0.0, and I hear the meter beep, I'm going to be like, ooh, time to start pulling the conduit and pulling the tape back and be like, what is going on right there with the wiggle test? The wiggle test in automotive is different than the wiggle test in other professions. All right, so we're not talking about we're wiggling the harness and we're wiggling things. And I've even seen sometimes where, if it's a sensor, you might do the tap test. And then your meter, if it's on min-max, might be like beep, beep, and you'd be like, whoa, it lost power for a second. Like, let me do that again. And then if every time you tap on the sensor, it loses power and it sets min-max and you hear a little beep, you're like, I think I found the problem. Make sense? See, I went through school, all the proper channels, and it was a long time ago, Cavalier, that you got in and the instrument panel wouldn't work. And it was like, oh yeah, I'm going to have to check and measure and thing and get my highlighters out and trace the diagram. And you want to know what the line tech did? You'll never guess. Banged on the dash like a chongo, like a ape, like a gorilla, like boom, boom, boom. And all of a sudden it worked. And I was like, whoa, is that how we do it here? And he's like, and it came on and I was sort of like, so what's that really mean though? And he's like, oh yeah, the circuit board and those instrument panels breaks a lot. And if it's kind of broken and you hit it and it starts working, you just order the instrument panel. And I was like, all right, cool. See, coming out of school, I'm not saying necessarily jump in the car and start punching stuff, but I'm saying like know what tests to use, and it's not just test it. Sometimes you're moving stuff around and wiggling, and and then you're gonna find it, and you're gonna get promoted. You're gonna make your dreams come true. Cool. So that's min-max. All right. So let's link why we're gonna do some of these. Remember, input, process, output, right? The ECU gets a bunch of inputs, and that was the thing you guys were just talking about. So if we have a problem with an input, we need to extensively be able to test, is the input good or bad? Okay, it makes sense? So let's just say, you guys remember this, right? This is the ECU, and every arrow that's inward is an input. Those are your senses or your sensors. Cool, so let's say, for example, we were to just talk about crank sensor. Now this class is electrical, so we don't usually get real in detail on the sensor. That's more when you cover engine performance. But the thing is, when you do transmissions, you need to know about input shaft speed and output shaft speed. And then when you do ABS, you need to know about wheel speed. When you do, you could just keep naming them off. If it's steering, you're going to need to know about the steering angle sensor and ride height sensors, right? So we won't cover really specifically any one sensor, but let's just make it, in this case, like a generic speed sensor, okay? how would I know if the speed sensor is giving me the signal or that I'm supposed to get or not? Well, let's just say I could use my meter, and this is the point where I'm gonna actually switch over and show you on screen how we would measure this. I just got to make my plan here. I'm gonna pull power, which I think it can handle. I'm gonna undo HDMI, and we're gonna change over to this right here. We should be pretty rocking. All right, and I'm gonna drag this over. Oh, there's another something. I think I can make it. Here we go. Get rid of that. Pull this over. Pull this over here. Make sure we really love that. Okay, pretty good. Good. X. All right, looking pretty nice. Okay. All right, so I think you guys can see this pretty well. Who remembers this little circuit board?
I do.
All right, but you might not have understood exactly what we were doing when we did this because you go through the steps and I'm kind of like, they need a little bit more. This generates different signals. So let's just say, well, we can start with anything you want, really. I'm going to make the ground connection, which you should remember. These are a love-hate relationship, these little boots. It's like it protects you from shorting stuff out, but they can be kind of a hassle. And then let's go with, I don't know, we'll start right here. And then if I turn the meter on, let's see if we've got any sort of voltage. All right, so I got 3 volts. So that'd be a good way to measure voltage, but what do we really need to measure? Well, I don't know. Let's say it's a speed sensor. And I wanted to measure, it's an AC speed sensor. I want to measure AC volts. I would have to come down here, and I would look at this, and actually we're going to jump this over here because this one's for AC. And I'd be like, is this sensor working, yes or no? I would go here, and I don't really see a whole lot of info. Oh, is this sensor putting anything out? Looked like it did for a second. All right, I'm going to center these, but we might need to measure, I was thinking hertz would be good. We don't want milliseconds. I was really thinking voltage. Okay, we got some small measurement there. I noticed we got something. I'm not totally sure that was good or bad. How would I know if it's good or bad? Think back to what I just told you. Yeah, I'd have to go to the spec. So if they're saying we should get 0.2 volts, I'm occasionally getting 0.2 volts right there, right? You guys couldn't see it that well, but if I'm getting 0.2 volts and that's all it called for as a spec, well, now I can get 0.3 once in a while. I'd be like, yeah, maybe that sensor's working or not. Let's say I'm going to center this one too. Okay, let's say the spec was 5 volts AC. Can you see that okay?
Yeah, that's not good.
Oh, so it's a fail. All right. And I might not exactly know really why, but if a sensor is supposed to put out 5 volts AC and it's only putting out 1, that's not good. But let's say we wanted to check a little bit better. Maybe we should be able to most likely check hertz. There you go. What do I have for hertz right there? What if the spec is 60 though? Then that would be like, okay, I found an issue. I might not know exactly why. All right. And then what if, let's just say, oh, the spec was 60 and look what I've got now. Okay, so that'd be good, right? Or if it was saying a minimum of 60. If a lot of times they'll give you like, they want 60 hertz plus or minus 10 hertz. So that would be like, if it was 60 plus or minus 10, what would that mean?
You can have 50 or 70.
Exactly. So that's like, I'll take $60 plus or minus 10, which means I'll take as low as 50, but I'd also take as high as 70, right? Make sense? So if they give you a spec and they're saying 60 hertz plus or minus 10, and you measure it like that, that's a pass. Cool. But if you didn't flip it onto hertz, you couldn't really tell if it was good or bad. what if we jump over to DC? So if I check DC, I need to move this to DC, right? Okay, good. All right, I got 2.46 volts. Good or bad? I don't. Exactly. There you go. Exactly. I don't know because I haven't referenced the spec. Make sense? We need to know the spec. Then if I wanted to do hertz on this one, let's say they gave me a spec in voltage, I could know. But if they give me a spec in hertz, I actually have to take a look. This is making almost 1,000 hertz. There you go. There's your 1,000 hertz right there, right? But if I just put this meter on DC volts, I'm not measuring hertz. You have to actually press the right buttons to measure hertz. There you go. 1,000 hertz. Good or bad? I really don't know. I'm just showing you how to set the meter up to measure what they're calling for. Makes sense? Part of the battle is finding out what the heck they're calling for. And you can see how it can vary. You know, we can get different numbers. Or let's say, how about duty cycle? Remember the on-off time? If we have our blower motor switch at the middle, what do we expect for duty cycle again? 50. Okay, so let's try to do duty cycle. I'm going to press this. Oh, look at that. Duty cycle. What do I have? 50%. What else can I get? Let's say I go to full speed. I don't remember which one of these is duty cycle. And actually, from what I recall, I don't think this changes all that much. I think it mostly stays right around 50, which is fine, but at least you know how to measure duty cycle. Now, if you were just turned on to measure volts, you'd be like, oh, I got 2.47 volts, but I don't know what the duty cycle is. So is the blower motor getting the signal correct or not? I don't know. I'd be like, oh, no, I need to measure duty cycle. There you go, 50%. Oh, perfect. That's great. And also, you can make the trigger negative or positive. Sometimes we're measuring the positive. If we're measuring the positive, when we power it, it's going to be measuring the positive as a positive trigger. But other times, the motor may get positive all the time, and we're actually triggering it with the ground time. So you'd have to actually change it over to a negative trigger, and that's on here as well. Let's see if I can change it between the two. If I'm on, there's a trigger negative. I didn't see trigger positive. Okay, so you see how your trigger positive is different than your negative? So I was actually on negative, which is fine. No problem. All right, what if we needed to measure an injector? An injector would be actually milliseconds. So I could press this button until there's hertz. We don't want hertz. There's duty cycle. That's the percentage. So you guys can see. Hopefully kind of see. What about, let's go with, there's milliseconds. So if we have an injector, let's just say, and we're trying to determine if the injector is getting powered or not. Like I mentioned this last time, if we go to fix an engine, it's a 4-cylinder, and cylinder number 3 is not firing, and we think it could be an injector. Maybe we listen to the injector and the injector is not ticking or clicking. We might be like, well, is the injector getting powered or not? The basic way is to plug a little test light in there. They usually call it a Noid light, and you'd look at the Noid light flash, and you'd be like, 2 flashes, 3 doesn't flash. Injector 3 is not getting a signal from the ECU. You could do that, but I wouldn't even spend the money on Noid lights. When I first got a meter, I didn't totally understand this yet, and so I got a meter that had built-in Noid lights, and I thought I was so cool as an OTC meter back in the day. Now I realized if I got the Fluke, I could have measured the milliseconds of on time, and if injector 2 was 3.1 milliseconds, and I moved over to injector 3, what do you think it should be? About 3.1 milliseconds, and if it was 0, it's not getting a signal, right? It did the same test a Noid light does, but I didn't have to buy another thing. But to be honest, a lot of people don't realize, myself included, by the way, I didn't realize the meter can measure a lot of stuff like this. You just actually have to press the right buttons. Kind of cool? Makes sense? Mm-hmm. So if you guys will remember, so we did, I think, everything I wanted to do. I'm pretty confident. Yeah. If you guys remember this, I'm going to show you why you would do these tests, and then you'd be like, oh, okay, I'm going to do those. Let me flip this back over, not drop anything, potentially. If I go right here, Then I'm going to switch this back over to HDMI like I want to. Okay, right there. I just need my power. And you guys are going to get to do some of these today, so that's fun. Some of it will be a little bit of review too. Good. And where is my HDMI cable? What's that? What's that right there? No, something else. Something. It's an Ethernet. I think it's this one, yeah. Yeah. Okay, there it is. Just a little stuck. I struggle with spaghetti wire a little bit. It's all right. Okay, here we go. We're going to be back in action. Share, screen 2, share. All right, so if we're back, let's see if you guys understood what I was saying. If we wanted, let's say, we're done with this. I could drop this down. Let's say that we were going to, oh, it's this again. Yeah, you know that was coming. I need to turn that off. That's how I keep track of my times. All right, so let's just say we wanted to test that speed sensor, and we looked up a spec right here, and that speed sensor was calling for, well, let's make it simple. Let's say it was calling for 60 hertz. How could I tell if that speed sensor is working right or not? Exactly, that's it. So I would probe right here, and I'd set the meter up to measure frequency, and I'd know whether or not it's getting 60 hertz. That's it. It's pretty simple, huh? Mm-hmm. Okay, but other people like to make it really complicated. Or let's just say it was like that extreme case like with my mentor, and he measured it and it checked out, but you thought it might be damage to this actual gear right here. How would you, exactly, then you'd go for the scope, do a picoscope, oscilloscope, or whatever, get a whole waveform. You can, everything that the meter does, the oscilloscope does, except it puts a picture on it, so you can evaluate really what you got. Make sense? Mm-hmm. And so you could do it fairly easily, not even really all that tough. And there's some other sensors here, but we'll focus more on those. So again, if you picoed it, you get a waveform like this. This is our AC voltage waveform. When we get into that pico, just understand there's a lot of different types of leads. So that's one of the coolest things about Pico is they make a really nice kit. On one end of it, you're going to be able to connect to the meter. But on the other end, like look at this long, tiny little probe. Why do you think you might want something like that? Yeah, it's really nice for back probing. They can be really nice for back probing. Now, if I were to really go, we could spend, I promise you, a whole day on what a picoscope could do. They have attachments that are inductive little fly swatters that you can hold over a coil, and it will, when the coil fires, it can actually induce an electromagnetic field, and the pico will pick up on that, and it'll graph the voltage, and you'll never make one connection. You just hold it near it, it'll pull a waveform up. Like Pico's got some really amazing stuff. For now, we'll keep it a little more simple. Yeah, if we're going to back probe, like remember how we were going to check that speed sensor, we would use a nice back probe like this perhaps. And if we were going to try to check that speed sensor, where would that back probe go? Right there. But that's terminal, I don't know, what terminal is it? I'm going to show you also how to dig the terminal up so you can actually probe it. Cool, and then you'd carefully probe it so you don't damage the terminal. If you work on diagnosis and then you fix the one problem, but the car leaves with 5 new problems because everything you back probed was damaged, you're fired, quite honestly. Right? And so when we look at this waveform right now, there's a couple things you need to know. It's a way for us to see the signal, to see if there's abnormalities. A lot of times we can record it. So like here's a really cool thing. Let's say you're working on a vehicle and you think it's got, let's say it's, let's go with, we'll go with that speed sensor. You think that speed sensor is good, but you're not exactly sure. You can actually take a measurement on Pico and save it as a file, and then you could upload it to a forum probably wouldn't be a forum. It'd probably be more like a professional page, such as like technical assistance. You can send them the file. They can take your file, open it up, and they can look at a file from another car. How cool would that be? You can compare your file to another file. Then you can really tell if it's good or bad, right? So you can't do that with a meter. You can get a number and be like, hey, this is my number. But if you want to really see the whole thing, you actually would need to use like something like a Pico or an oscilloscope and get a specific file saved to compare to another car that could be in another country if you wanted. Somebody else could do the same thing on the same program and then look at them side by side. So it's a pretty cool function. And then when we look at waveform stuff, you see this yellow square? What do you think these numbers are? Anybody think they know? Yeah, so that's going to be our voltage. So if we wanted to measure something that was going to be 5 volts, anywhere between 0 and 5 volts, we generally want to set this left side up to be maybe 0. You might even go like a little negative just to get it up a little bit higher, and maybe 5 volts. But if we're going to do a sensor that's between 1 and 2 volts, you could do 0 and 5, but what's your waveform going to look like if down here is 0 and up here is 5, and the sensor's only going to be between 1 and 2? Yeah. And are you going to be able to see it as well? No. Right, exactly. So truthfully, the only reason that we mess with these numbers is to get this thing to look the right proportions. That's it. Make sense? That's all. But how do you do that? Well, there's a couple ways. One, you can be familiar and you can set it up based on your knowledge. That'd be kind of abnormal. 2, you can look in the service manual and it will tell you. Set this scale up from 0 volts to, like in this case, 2 volts or 3 volts or whatever the number is. Oh, it's actually 0 to 1 in this case. Set up your voltage scale 0 to 1 volts, and that's going to replicate this exact shape if it's good though. See, where it gets complicated is you'll set it up and you'll be like, no, it's a flat line, and you'll just get in this loop of adjusting the scale. Like you're going to adjust the scale all you want. If the waveform is defective, you can't make it not defective by changing your scales. Make sense? And then what do you think these ones are down here in this yellow box? Exactly, time. So if on here we've got 1 millisecond, this is 0, this is half, this is 1 millisecond. What if we made this like a 0 and this a 5 and this a 10 and this a 15? What would that waveform look like? Yeah, like really scrunched in together, and you'd be like, I can't really see if it's good or bad, right? So it's so simple. All we're really doing is adjusting your voltage scale and adjusting your time scale. You just have to know what numbers to put in. So when we go up to Pico right here, that's what some of these little boxes are. It'd be like voltage, AC or DC. In this case, AC, 0 to 1 volts. Time, let's do each division, which is each line, let's make it a half a millisecond. Once you set it up like that, you're just literally going to probe it the same as you probe voltage. So how you saw me probe that little chip, that little circuit board, same thing with an oscilloscope. Put the ground on the ground, you put the positive on the voltage that you want to measure. Make sense? And it's just like that. It's really easy. You guys could definitely do that. So this is just saying the division, the scales, voltage per division, etc. If we were to look at this, we're going between a negative, I don't know, maybe a negative 1 volt, and maybe this one's up to about like a positive 1 volt or so. You could rescale this a little bit, but if in the manual it says to do 0.4 volts per division, you can do that and it's going to look just like this. If you were to do 0.1 volts per division, this thing would end up really huge, which is fine actually if you want to look in detail. But typically what you're going to do is you're going to look in the service manual. It's going to give you this waveform should look like this. And if you set yours up differently, you're going to be like, mine's different. I found the problem. You'll be like, no, you just didn't set it up right. You know, that's all. And then you could see just a couple more of the controls up here. We usually keep it on auto detect. That way when it sets up, it'll check automatically if it's AC or DC. But you can manually make it DC. You can manually make it AC. and this is one channel. You see the blue? If all you really want is to measure one thing, you just use one channel. But what if you wanted to measure two things? What if, let's say, we had that wheel speed sensor, and you're like, you know what? Let me measure the right front and the left front at the same time, and that way I can compare them, because they should look pretty similar, right? If you're going straight, they should be the same speed. If you go around a turn, you know the inside track is going to go a little slower and the outside is going to go a little faster. But if you're going straight, they should be identical. How about we make blue channel 1, the left front? We could also probe channel 2 as the right front, and you could have them both on screen, and they should look pretty much, they might not be perfectly in phase, but they should have the same peak, same valley, and they should be switching about the same amount. They might just be not exactly lined up. Then you could get into like setting a trigger to try to pull them one over the other, and you could do some tricky stuff, right? But this is the Picoscope interface right here. That's it. So what if we wanted to adjust our voltage? If you look up here, it's actually set to auto, but we could manually make it 0.4 milliseconds per division. What if we want to change our time divisions? You could go up here. What do we have here? What's that number? 50 microseconds per division. And is that true? Yeah. Negative 200 to 150 to 100. Yeah, that's 50 microseconds per division. It says it right there, microseconds. That's it. You just literally use these little drop-down boxes. Change it.
I thought micro was the freaking upside down H.
Oh, you're right. Milliseconds. You're right. I couldn't see that good. Called me out. Called me out. He's right. Woo, got him. Yep. Yeah. No, you're right. Micro, you guys know that symbol?
It's upside down H, right?
Yeah, they call it like a muth or something.
It looks weird.
It looks like Pokemon.
Like that. Yeah.
Yeah. All right, good. You guys got it so far. So there's your, right, that's what I was thinking in my mind, right? Here we are changing AC to DC. Here we got our time division, 500 microseconds per division, which whatever it calls for, that's all. And then again, we can, if you do this raw, this waveform is going to be moving all over the place. And you'd be like, I don't know, I couldn't really see it. That's when you'd set a trigger, and the trigger is essentially just really going to anchor it. You could say like, start triggering at 0.8 volts, and it'll make it a little more stable. Another trick on Pico, you can actually not even trigger it, but you can hit the space bar, and it'll just screen capture it. It'll just pause it right there, and it'll give you an image. Right, so that's a nice function too. Right, and here this is what it's saying. You know, you can change. Do you want all the things that we measured on the meter? Do you want this to look for AC voltage? Do you want this to look at frequency? Do you want this to measure duty cycle? What is it, right? So we can do all those adjustments right here. It's kind of the same as when we press the buttons on here, but there's no buttons. You're using the drop-down menu and setting it up for what you want, right? And then again, like this is a non-Pico. I believe this is actually the snap-on. They're fine. It's good. You can get a 2-channel. That could do 2. You can get a 4-channel, and then you can have 4 different things on the screen. Like this one's a little bit hard to see. I don't like the black background, but this one has 4 different channels running at one time, which this is going to be a little bit hard to explain, but I'm going to go for it. If you're trying to tell, let's say you guys know timing belts and timing chains, right? You know, once in a while you can have a timing belt or chain that like jumps a tooth or several tooth. Or let's say someday you're the chingon shop foreman of your dealership. It could be you. It's true. And you got a brand new technician and they did a whole timing belt and timing chain, and now the car runs bad and you think they didn't line it up. Is that possible? All right, so option 1, the old school way. You go ahead and you tear it down and you're like, you see, this belt was a tooth off, you ding dong. But you got to tear it down. You might be hours into this. Like especially if it's a V6 timing chain and a front wheel drive like a van, you're going to pull the engine to pull that apart. I would rather not. If I could take my oscilloscope and I could graph out crankshaft, camshaft bank 1, intake and exhaust, camshaft bank 2, intake and exhaust. I mean, that's up to 5 channels, but you could probably do it with maybe just crank, intake, exhaust, and intake, you could compare that to a known good waveform, and let's just say your exhaust bank 2 was supposed to be here, but it's over here. Then you know it's off, right? But let's say that your exhaust camshaft was supposed to be here, and it is here. And intake is supposed to be here, and it's here. If you look at it, you can see if they're all in alignment, not of each other, but of a known good, you'd be like, no, the timing is good on this one. But if it's actually skewed off, you'd be like, you see that one right there? Your intake cam on bank 2 is at least a tooth off. So what do you know you have to do now?
Take it down.
Pull the engine, pull the timing cover, pull and redo all that stuff, right? So like you could get really, you could get really advanced on multiple channels of Picoscope. And that's sort of what this image was supposed to show. It's just you can't see it all that well. The other thing it can show is like multiple ignition coils firing at once, or multiple injectors firing. If you had a 4-cylinder and you graphed using a 4-channel oscilloscope 4 injectors, you can see all 4 of them firing at the same time. They should all look the same. But if one of them looks a little different, you can interpret what the failure would be. Same with ignition, primary coil, secondary coil, like that's all engine performance stuff. But just know a multiple channel oscilloscope can graph a lot of things at once, and you can do some really good diagnosis without just tearing it down. Cool. And then like we were talking about broken teeth, so this just gives you a visual. Each one of these teeth make a high mark on the waveform, and then when there's a gap, that becomes a low. And then when there's a small tooth, that becomes a short waveform. And then if one of them's damaged, it'll have a defect, right? So like this actually has a defect. If you were to scale this correctly, you could see, oh, you see that there's like a drop down right there? That one's cracked. That's a cracked tooth. That's a hard diagnosis right there. You could be like, I got to tear it down. I got to pull it apart. I got to do this. But like the Picoscope could illuminate it for you and be like, yeah, we got a cracked tooth on there. What do we need to sell? It's not a sensor. We need to sell this reluctor wheel, that sprocket, whatever it is. We need to sell that. We verified it because we could see it. Cool. And then also, a lot of the scopes have different attachments, like I was saying about that wand. They can do things like measuring amperage. So sometimes what we really want, we can measure voltage on an injector, but sometimes what we'll actually measure is the amperage on that injector. And if we measure the amps on that injector, it can tell us a little bit more about what's going on. So if you want to measure amps on a Pico, it's not like the meter. You don't put it in line. You don't open the circuit and put it in line. You're actually going to use like an inductive amp clamp. So this amp clamp would go around whatever you're going to measure. These leads can connect to a meter, or they can connect to the Pico, and it'll essentially what it'll do, it'll say like 1 amp is equal to 1 volt or something. And so you'll look at your screen, it'll say volts, but you just have to know the inductive clamp is converting 1 amp to 1 volt. So if it shows 0.5 volts, it really means 0.5 amps. The reason that the Pico can be nice for that is things like coils, they don't just flow a certain amount of amps. They'll like ramp up or ramp down, and the shape of the ramp can tell you a little bit more about the defect. Makes sense? So like if the ramp is supposed to be like this, but the ramp is like that, you'd be like, whoa, that ramp is off. It's just another way to compare it to a known good. Right, so let's nail this down on a diagram. You can get some perspective here. All right, let's say we are testing a blower motor. Right, if you look at this, you can see, let's go over some of the parts of the diagram. You can see, here's our fuse. Here's a couple more fuses. What's this thing? It says right there, AC amplifier assembly. Let's rename that. That's going to be the AC ECU. That's the computer right there. The computer is going to control the part that we're worried about, which is right down here. Blower motor subassembly with the fan. So back in the day, the blower motor was just the motor. And the blower motor worked in conjunction with the blower resistor, which was kind of like it was like it was a resistor with different circuits, whereas if you wanted speed 1, it would send it through a bunch of resistors, and you'd get low voltage and low amps to the motor, and it would turn slow. Then if you wanted high speed, you'd bypass the resistors, and it would go straight 12 volts, right? We don't do it like that anymore. You ever notice when you get in the car, a new car, you ramp up the blower speed, it like gradually increases, and it's not notchy. And also, you know, automatic air conditioning, we're gonna want that to be automatically controlled. You can't have it be automatically controlled if you got to go in there and move a knob, right? So we're doing computer controlled. The way we do computer controlled is we're going to use a blower transistor, it's called. So right here where it says blower motor subassembly, you've got 12 volts coming in from the fuse. You've got ground on terminal 1 going to the chassis ground. What the heck is that? What is SI? That's the signal. Signal. What generates the signal? Bingo. So the computer is going to generate the signal. How does it generate the signal? Well, that gets back to last time. Input, process, output, right? So what's the customer want? What's the outside temperature? What's the inside temperature? What's the solar load? What's up with the windshield? Is it fogged up? Like, it's going to look at all these things, and then it's going to generate a signal. Let's just say this is going to be duty cycle. Give me a signal, and that'll be our baseline. What signal do you, as the ECU brain, want? 50. I like it. All right, so when it generates 50, it's going to put that out on that terminal. What terminal is that one?
22.
Terminal 22, and the A is connector A. So there's one wire that comes off of the ECU chip, and it's going to have 50% duty cycle in these conditions. You understand? And that one wire is going to carry that 50%. It's a red wire, and it's going to show up with 50% duty cycle right there. And if it does, what do you think this blower motor subassembly with fan will do?
Spin at 50.
Exactly. It's going to pulse it. So there's a transistor in there, a big MOSFET or something transistor, and it's going to basically take the 12 volts right here, the B+, and it's going to send it to the motor half the time. It's going to go on, off, right? Or sometimes it gives it 12 volts all the time, and it's going to pulse the ground, on, off, right? But this is almost like its own little mini computer down here. But this computer doesn't make decisions. This just pulses a transistor to control the blower speed. Cool? So back in the day, you'd be like, yeah, does it have 12 volts on 3? Yes. Does it have ground on 1? Yes. It's bad, but there's a third wire on here. What do we need to verify on that third wire?
Signal.
How? I agree, but how? You could do it like that. Truthfully, if you get sketched out on this, you could go to 22 and 2 and measure the resistance of that wire. But if the wire's good, you don't know if it's the module not giving the 50% duty cycle, or if it's a bad blower motor subassembly that has an open transistor or something, right? So resistance is good. I like it, but that's not going to be the best tool in this instance. You could pico it too. So if we went with a pico, we should get a 50% duty cycle at 22, and it should carry it all the way to 2. Personally, I'd probably check at number 2 first, because when I run into a car like this, I'm thinking probability-wise, right? It's either a bad ECU, a bad wire, or a bad transistor in the blower motor, or the actual motor itself. I'm kind of betting on that blower motor, which is why some techs will just be like, yeah, do the blower motor. And if it doesn't fix it, then call the foreman and be like, okay, you can do that, but the foreman's going to be kind of irritated. I've had foremen too, and I'd be like, hey, I need help, and they come down and be like, what have you done? And I'd be like, whoa, like, what's up with the 2, dude? And he'd be like, what have you done? I'd be like, I checked this. I checked 12 volts on terminal 3. I checked ground on terminal 1. And right here is where I'm kind of stuck. And he'd chill out, and he'd be like, oh, okay. You're being thorough. All right, I'll help you. You know why he's kind of got a toot already? Because the last tech was like, I haven't checked anything. That's why I called you. It'd be like, dude, like the foreman's there to help on some problem cars, not throw 25 people on the they, them, he, her, their back and like fix everybody's diagnosis all the time. Like, no, that's not, you want to talk about irritating? That's ridiculous. And I don't want you to be like that. I want you to be like, I think I can diagnose it, but once in a while I need help. That's my goal for you. Then you'd be like, I checked all this, but I was a little stuck. How do I check the signal? Foreman's like, yeah, you're right. Do the pico. Bust the pico out. You're going to do your ground on the ground. You're going to do your red terminal on terminal 2. It's going to give you a waveform like this. If you got a waveform like this and you got it set at halfway and you're expecting 50%, wouldn't you say this is a good duty cycle signal? Mm-hmm. All right, so what I'm telling you is this part, blower motor subassembly with fan, has 12 volts, it has ground, and it has a nice clean 50% duty cycle. What's wrong? Blower motor's bad. It's got everything it needs to work. What is going on in there? I don't really know. I just know it's got everything it needs to work, right? Mm-hmm. Just like I told you with employees. If you hire a lube tech and you give them the oil, you give them the filter, you give them the bay, you give them the tools, they got the torque wrench, and they still can't produce the car, you got to get a new employee. Now, if you got an employee and you don't give them the oil and the cars aren't coming out with the oil changed, you can fire that employee and get another employee. Guess what's going to happen? Still no cars are going to get their oil changed. Makes sense? So that's all we're really doing. You could throw a blower motor in there and it may or may not fix it because you really did no diagnosis or assessment of the situation. So, but hack right here, quick tip, pro tip, you could go to terminal 2 and you could use your meter. And what could we set this meter up on? Yeah, you could literally, well, we're measuring duty cycle right now. So you'd go to the percentage duty cycle and it'd be like 50. You'd be like, chilling, I'm good. Is there some minimal, minuscule possibility that like one of the teeth is damaged or something? Maybe, but understand those teeth aren't the teeth, right? We're going to call the highs and lows the waveform. That's being generated by the ECU. It's not being generated by a spinning wheel or a sprocket or a reluctor, right? So when it's an ECU generated square wave, I don't usually look at it on the Pico because it's like, you know, if I get 50%, I'm good. Now, if it was a sensor that's reading a wheel, a spinning sprocket, I might actually want to Pico that because I want to see is a tooth damaged. But when we say a 50% duty cycle like this, understand the ECU is generating that square wave. The ECU, essentially, this is parts out of an ECU. This will generate a beautiful, nice, clean square wave because it's digital. It's a transistor on, off, on, off. It's not going to have the weird defects of a potential broken reluctor wheel tooth. Make sense? So I'm cool with just the meter in that case. I'd run the meter on that all day. What if, however, go ahead, hit me.
So would doing like min-max on the meter, would that do anything? Would that be able to check?
What's interesting is if you look at this, let's say this is a duty cycle that's going to be a 12 volt on and off. See the 0 and the 12? What do you think the min is?
0.
What do you think the max is?
12.
So it kind of tells you there's some sort of a 0 to 12, but it doesn't really tell you like, is it generating a good 0 to 12? In this case, min-max probably wouldn't help us out. However, let's just say that blower motor was working intermittently, and I went down here and I got 12 volts on B+, but once in a while I'd hit a bump and it would stop working. I might be like, it could be the motor, it could be connection, but couldn't it also be a problem on this white wire? I could put my meter on min-max and I might get 12.6. If we're driving, you know the voltage is going to be like 13.5. Let's call it 13.5. If I'm driving down the road and I got 13.5 on terminal 3 and then I hit a bump and my min-max goes off and it dropped to 0, what's that tell me?
The wire's faulty.
Something up here is faulty. Yeah, so min-max is amazing, but not so much for duty cycle. Min-max is good for intermittence. So if I drop to 0 volts when I hit a bump, I might need to go do the same road test and I might need to move my meter to terminal 3 and hit the same bump, and I hit the same bump 10 times and it never drops to 0, then I know it's getting a consistent 13.5 to here, but it's losing it between here and here. I've narrowed this intermittent problem down to between terminal 3 of this connector and terminal 3 of the fan, you know, and then I might have to narrow it down more and again, right? So min-max is cool. Does any of this sound like it's going to be an easy, clean, you pull the car in, you put your hand on it, and you know what's wrong with it?
No.
I'm describing cars that are hard to fix for seasoned, well-trained, certified technicians. You know what happens when they struggle to fix these and it takes days and they think they fixed it and it goes back to the customer a few times? You want to know what happens on those? Lemon law. Lemon law. So that's what I'm saying. So like I'm just letting you know, there's some careers that I wouldn't put a lot of stock in and be like, you're going to be a journalist. I'm sorry, AI's taking your job. Just letting you know. You want to fix this piece of crap that's about to be lemon lawed. If you can fix this, if Honda has to lemon law that car, understand. They're paying attorney fees and legal things. It's going to court. They're paying several representatives to try to defend them. It's already been at the dealer. The dealer's got money. Honda's got to pay the dealer. The dealer's saying they want more money. The tech wants to get paid. The tech spent 4 hours on it. And Honda's like, well, what'd you do? And the tech's like, I tested it. And they're like, what'd you measure? And they're like, I tested it. Like, what was the voltage? I tested it. Like, I'm not paying that claim, but like, then they got to buy the car back for whatever the customer paid. So if it costs Honda 15 grand to make the car and they sell them for 30, they probably do, maybe more, I don't know. They probably make good profit. They don't get to buy it back for 15. They're going to buy it back for 30. So Honda's already upside down 15 grand plus the dealer cost, plus the legal fees, plus the whatever, plus the other thing, and plus the customer's like, yeah, but I got interest on that loan. I need the interest paid off. Now they're paying the bank's interest. That may very well be a $50,000 loss on one car. So if you roll up and you're like, you know what, these buybacks, I can fix these. They'll be like, here's your job and here's your pay and here's your money. So remember I told you a student who that's what he does now. They gave him, I think I told you, he's only like 26. They gave him a truck, a gas card, insurance, and they send him all over Southern California for crap like this. And he can't necessarily fix every car, but he can go to the tech and be like, if you hit a bump and it goes out, let's look at the diagram together. And he would interpret it the same way I would and say, well, if you could be losing 12 volts at 3, you could be losing ground at 1, you could be losing signal at 2. These are all could be. You got to nail it down. What is it? Not like what's possible, like what actually is it? And then once in a while, the manufacturer will be like, you know what, just replace this, and replace the harness because we can't afford to take any more guesses on this, right? So sometimes they'll throw a bunch of parts at it, but you know, this harness can go all behind the dash and stuff. It's going to be a mess. You don't want to really do that.
Oh, I mean, you do a whole interior harness?
Outside work I'm cool with. Inside work, not my favorite. No, I'm not even, nope. I'll do it, but I don't want to.
Yeah, if you get the headliner dirty, replace it.
Yeah, and to replace it on some things, cut the windshield out just to put the new headliner in. It's a nightmare. But this is a good example as to why we would put out some of those tests, right? If the car's got a symptom, you got to know what to actually do. But you wouldn't just be like, oh, the customer wants me to check their duty cycle to their blower motor. You get what I'm saying? All right, so let's flip this to a little bit more Pico-specific stuff. I think you guys will like this. This is not part of the presentation. This is just a straight-up website. This is on Pico. You could go on here anytime. I just got to pull this other page over. And I really like this because they have guided tests that are available to you at all times. So guided tests. What do you want to test? All right, first off, why would you even be on here? A lot of times you'll see in a moment, like the IN might not guide you to do some of these. You're outside the box when you're at this level. As soon as you're having to do some of this stuff, you got a reason you're doing it. Next one's going to be higher. Oh, I want to bet? You can keep it until you start talking again. You get another one. You'll have a whole collection, but you might get a little bruise out of it. All right, let's say, what do you want to test?
Sensors.
All right, cool. Let's click on sensors. This is outside of the manufacturer service info, but it's legit. All right, so it's going to give you some info here. I'll even zoom in. Let's say, remember how we were talking about crankshaft position? Mm-hmm. Here's how to test it. Let's say floating or running. Let's go with, all right, here you go. Talking about set your Pico up like this. Where's the ground going? Yeah, like to any shiny metal piece that's chassis grounded. Cool. Where's your positive lead going? Oh, and this is interesting. They've actually got a couple different wires on here, but we're going to mainly focus on this is going to go on your positive. So all we're really looking at is what's your voltage doing. So remember, when the tooth goes by, it should be a high, and then when there's no tooth, it should be a low. So that's all. We're measuring available voltage essentially, but it goes to this little box, and why don't we see any measurement here?
Because you have to go to the laptop.
Yeah, exactly. So then you hook it up to a laptop, and then you actually get a waveform, right? So remember, this is looking at these teeth. This is an example. Okay. All right. Does this look weird or what? What the heck is that? All right, I kind of fooled you. I'm going to tell you. If you look at these teeth, right, each one of those is one of the teeth going by. But if you look down here, that's taking 20 milliseconds. What do we measure engine speed in? RPM, which is revolutions per minute. So the ECM is going to say, it can't measure exactly revolutions per minute, but what it can measure is how many teeth went by in one division, and one division is 20 milliseconds. So you had a bunch of teeth. Each one of these teeth is not a rotation. But if you just have teeth on teeth on teeth, that can tell you the speed, but can it tell you the position? It's just you're lost in the teeth. So what they do is they'll put a double gap. You see this right here? This is what tells you position. So if we were to look at that sensor or that wheel, look at that. That double gap right there becomes this. So now it can tell not only the speed, because it can count the teeth over 20 milliseconds, but it can also be like, all right, there, let's call that top dead center cylinder number 1. There's top dead center. So it'll be like, this is the speed, and then this is halfway to TDC, and then this is all the way to TDC. So now it can see speed and position. Make sense? If you roll into the service manual, as I'm going to show you in a moment, it may give you a waveform like this as a sample, and it may not. Sometimes you just have to know, this is how this type of sensor works. This is what I really want to see. But truthfully, once in a while, the manufacturers don't really give all that much info because it actually takes a lot to gather this info. You got to get a car, you got to get the Pico, you got to do the measurements, you got to save the file, you got to do a screenshot, and you got to do that for every single sensor, so the manufacturer doesn't always have it. There are times where I have to resort to, like, let me go on Pico or let me get a hold of technical assistance and let me see if I can get a good waveform from them, because the manual may not specify. Right, cool, but you guys can see this it's not like it's hard to set up. Just going to go here. It's going to give you some specs as to what settings we're going to put in. So we're going to say like plus or minus 20 volts, which it doesn't look like it quite went that. Yeah, it did. It goes all the way down to 20. Okay. It's going to be DC. Actually, it's AC on that channel. That's true. And then your time divisions, how much? 20 milliseconds per division, right? So we manually are going to set some of these things up, and then we're just going to take a measurement and then pause it. Cool. So that would be how to do one sensor. You think you could do that? Wasn't that hard? But we'll take a quick look at a few more, some guided tests, and then we'll jump back into like what terminals and stuff. Let's say you want to do like an injector test. Let's do a gas injector. We'll do old school multi-port injection. Okay, and it's going to give us a few warnings. Oh, look, that's how you do it right there. Okay, this, however, what's that clamp measure? Amps. Okay, so that's not measuring voltage. That's measuring amps. Okay. That's the ramp for the injector. That would be like a good ramp for that particular injector. I don't know what injector we're working on, though, so just saying like that would be a good current flow ramp. It ramps up, and then it flattens off, and then it drops down. That would be a good ramp. I believe, and this is even giving you some codes that it may set. So that's a good way to check the injector. What about, I was actually going to show you injector pulse, voltage measurement. Injector MPI voltage, there we go. All right, so you can see how we're going to set this up. Chassis ground, and then the red one, The red one, I think that red one may be actually on,
The base? Yeah, I think it's not the base.
I think that could be the negative actually. All right, so let's take a look. All right, so let's interpret this a little bit. We have 12 volts right here. So you think that that would be powered on, right? But if we're measuring it on the ground, if we're measuring on the negative, the on time is actually when it has 0 volts because we're seeing if it's grounded. Your on time is down here. Your on time is 4, let's see, that's milliseconds, I believe. So you actually have 4 milliseconds. Do you guys remember what we could do on the meter to measure that? You literally put it on milliseconds. That's all that meter will tell you is how many milliseconds that's on. That low part is on time. So if you go wide open throttle, this milliseconds will actually grow to maybe 6 milliseconds, right? Your meter could show you 6 milliseconds, and you could tell the injector is getting 6 milliseconds of on time. However, when we take the ground away, it's going to actually break down an electromagnetic field, and so this can actually tell us a little bit more info too, but you can't get that out of the meter, right? So we could compare this to a known good. Sometimes this can give us an information if the injector is sticking or something like that, right? So some good stuff that we can do, and again, it gives us some of the settings to put into the Pico. All right, so anytime, go through, you can look at all sorts of stuff. Pico's really amazing because they're doing their own samples and waveforms, and ignition's really amazing, and even communications with like CAN and flex ray and all just insane types of stuff. They even have a thing where you can put your Pico on and it'll measure the voltage pulses and it'll convert it to hexadecimal code, and it can actually break down what the message is on the network. And I'm like, why? I'm like, honestly, why? I just need to know if the module's on the network. I don't need to know exactly what every pulse means. But this is used by more than just technicians. This is used by companies who are trying to make aftermarket products to get on the network to be able to do different things, right? So this is a rabbit hole right here. You've been warned. All right, but let's go with something a little more practical, like how I like to do it. I just got to click through. These are Picoscopes for sale. You can actually download the Picoscope program for free. Oh, bummer, I think it logged me out. No, maybe it didn't. Let's go with, if it did log me out, I may just have to pull it off screen. It did. It did. Let me pull this over here, get logged back in real quick. Bummer. Let's see. It's going to make me close that. Dang it. Pain in my butt. It's okay, actually. I've got one that's still logged in, so that'll work. Let's say that we wanted to test. I was going to test something here. I forget what it was. I think this is a blower motor. Yeah, remember the blower transistor we talked about? Here's the Honda test. Now, this is going to be maybe a little, I don't know. I'm just going to call it how it is, okay? If anybody's offended, you can file a complaint. When I went into the Honda test, I was really hoping to have a more advanced test. And I've kind of heard some of this, and I've known some of this, but typically, technicians don't really know what to do with a waveform. So Honda's actually said, we're not even going to put those in anymore. We're done with that. If you go to test this blower transistor, this is all they really want you to do. You're going to come in here, go to the transistor. You're going to go, you see these terminals? What numbers are those? Can you see?
1, 2, 3, 4.
All right, but what are we testing right here?
3
3
and 4.
and 4. We're going to go with 3 and 4. Just 1 second here. Okay, yeah, that's good. So we're going to go terminal 3 and 4, and we're going to test resistance. And what's the spec?
1.5.
Yeah, can you guys do that? 1.5 kiloohms, don't miss the K. Can you guys do that test? That's totally doable. What about 2 and 4? And it's going to give you some specs for 2 and 4, right? And it's going to give you some very basic specs and some measurements. And then it's just going to say, you're going to actually, I think it actually has this jump in it here. All right, they want a jumper wire from 22 to 17. If the blower motor runs, the power transistor's okay. They have you diagnosing this like in a way that's more easy, but it doesn't really show you everything. And that's kind of the trend of the industry, because 9 out of 10 techs are kind of like, I'm not getting the Picoscope out. I'm not measuring that type of stuff, right? So if you go in the IN, they're gonna give you, the only version you know is this. But the version I know back in the day, they'd be giving you all sorts of information so you can really understand the problem. But current techs, my techs have problems too, my age. But current techs like, no, I'm not gonna do all that. Give me like two, 3 tests I can do, and I'll do those. But I'm not gonna get out the Pico and graph it, right? So they're gonna give you the little bit more of the lame version, measure that resistance, measure this resistance, jump terminal 22 to 17. If it works, good. You got it diagnosed, okay? If that's all you want to do, you will be fine. You'll be average, maybe even better than average. But I'm going to try to take you to the next level, because that's my job. Let's say, and I'm going to jump over to this screen. Let's say I don't know Honda's system well enough to navigate it all the time. I'm learning it, but a little slow. Let's say we're going to try to do that similar test on, how about we'll do and I'll show you exactly how you'd go through and take measurements and diagnose it right. So we can go, you could look for all sorts of TSBs and stuff, but let's just say you wanted to go in for blower motor things. It's really just going to tell you how to change it. Everybody's gone away from giving you a lot of hand-holding guided steps. What I would really do is just go to the wiring diagram, and I'd have to look at it and be familiar with it. Then I would know where to go from there. So if I go auto AC, I'll full size this. All we need is a wiring diagram, then we can diagnose it. See, all data was just a chopped up version of this. It was just an irritating one. So that this whole blue box right here, that's the AC control module. What we're looking for now is a blower motor. Which I thought would have been over here. There's a control assembly. Okay. Magnetic. Maybe that's a good idea. That would be a no. I'm going to keep on trying. You know what's funny, when I prepped, I actually looked it up for a Corolla. So if I can find it quicker on a Corolla, let me just jump back over. That makes sense. Okay, how about we'll go with this. We'll go with this. There's a pressure sensor. That was close. Huh. Combo. Oh, what do we have right there? Okay. Looks kind of familiar, right? So if I rolled up to the car and that blower motor didn't work, what I'd have to do is be able to look at this and be like, what is going on here? The blower motor with fan subassembly is right here. Where does it get the power? Can you tell?
Battery.
True, but what terminal, right? So if something doesn't work, I want to think in terminals.
It's getting from terminal 3.
3, exactly. So I could go down there and I could just probe 3 and be like, yep, it's got B+, 12.6 volts on a fully charged battery, or a 13 something running. Where's the ground terminal?
1.
I agree, follow that down, that's ground. Cool. 1. Normal, a decent tech can do that. Where they'll get stuck is they'll look at this and they'll be like, SI, terminal 2, like what is that? It doesn't show you jack diddly, does it? You're like, what the heck am I going to do, right? So I'm going to show you a few pro tips here. I need a signal from that green wire coming from the AC ECU. I'm pretty sure it's going to be duty cycle, but I'm not 100% sure. What I'm going to remember, though, is it comes from terminal 2, right? B in terminal 2, and it's going to go down to terminal 2. So I'm going to show you what I would do next is I would back out of here. I'd minimize this. I'd actually have to jump over here. And every manufacturer's got a different way to get this information, if you can get it at all. And I would jump into anything, open it up. I'm going to go under heating and air conditioning, and I'm going to look for something called terminals of the ECU. And this is how to really get pretty deep in there and fix it. You guys see we've got all these. Does anybody see terminals of the ECU? Okay, maybe not here, but we're going to find it. We could go here. There's the AC amplifier. The system. Do you see that? So if I go here, this is going to give me a map of all those terminals, right? Do you guys remember which one we were supposed to look at?
B21.
Okay. Was it 21? I thought it
Yeah,
okay.
21.
All right, I believe you. All right, so if I go down here, but I think we would have needed to know this connector was showing up here. You're right, B21. Yeah, exactly what you said.
Oh, yeah.
I should have trusted you.
It's all right.
There's eyes. There's eyes. See, this is a little bit confusing for me right now. This is not showing B, but that's okay because I know about where it's at. M3. Oh, look at this. This is the one right here. Yeah, I'm a little weird as to why it's on 7. It could be.
This is a 21 blower.
17.
Oh, yeah, there we go. Right, so there you go. That's our connector that we wanted, isn't it?
Yeah.
It was 21. So how would we find that? You'd pull the 21, and then you'd actually this one got a little bit weird, but 140 I-49 terminal 21. Where's the location? I-49 is the middle connector, right? Where's 21 at? See that? And by the way, this is typically from the perspective of back probing, right? It's not where you disconnect it and put it in the front. It's where you leave it plugged in, and we'd bring our probe over there, and we could just go ahead and probe into that with a back probe, right? So you follow me so far? So you could probe 21, but what are we checking for? See, that's where we don't know yet. So when we find 21, oh, check this out. You see that waveform?
Mm-hmm.
That's what it should look like. And if it doesn't look like, let's say it was a flat line 0, you'd be like, okay, I'm not getting the right signal. Kind of makes sense? So once you get to this point, it gets actually really hard to figure out what stuff should be. So sometimes you resort back to like what you learned in school. You know, if you look at that and you say, oh, okay, it should be a square wave. This one didn't even give us all that much detail, but what's the tool setting? 2 volts per division, 1 millisecond per division. Remember how we looked at that on the Pico? Go ahead and tell 2 volts per division, 1 millisecond per division, and then it should look like this, but it doesn't really tell you if it doesn't look like that what to do, so it can get a little bit weird right there. Then if we were to interpret that, and it doesn't tell you this is for you to know, here's your blower fan subassembly. If we did that on terminal 21 and it was good, that still doesn't tell us what parts needs to be replaced, does it? It tells us that the ASE ECU is putting out the right waveform of a duty cycle. Where could we check it next?
Terminal 2.
Go right down here, and if you check it at terminal 2 and it's a flat line, what's wrong? It's really not that complicated, though. If you think, but it's hard to find somebody who will take you through the whole process. So you check it here. What voltage? It's not really voltage. You're looking for a waveform. Or if I wanted to cheat, advanced level, I would just put this meter on duty cycle and I'd get a measurement of about 50 if I'm on the halfway point. I'd be like, cool, I got 50 there on terminal 21. What do I have on terminal 2? 0. The wire's open. And if I really wanted, I could even split the circuit in half right here at this connector A16 at terminal 7. I could disconnect this and see, do I have 50% duty cycle and or a clean waveform coming in or going out? Because maybe this connector got some corrosion, or maybe it got a loose pin fit, right? We could lose it right there. There's cars being bought back right now, lemon law buybacks, for a loose male-female connection on pins. But which ones? There's thousands of them in there, so you got to be able to like track it down. All right, cool. Was that kind of fun? Did you love it or did you hate it? It's intense. It's intense. All right, that's pretty much all I have for you guys. We could apply that same lesson on whatever. Crankshaft position sensor, cam position, all of that stuff. You find out what the waveform should be. You check it here. You check it there. You see where it's losing it. If on that diagram we were to not get 50% duty cycle out of here, you know that we'd be probably replacing an ECM. You might check and make sure there's no codes or anything, but like probably ECM. If it was getting the 50% duty cycle down here, you're replacing the blower motor sub-assembly. Cool? You guys got it. And we're there.
Where is it that we go again to check for the wavelength?
That's the problem. It's hard to find. I looked pretty hard on the Honda IN, and I really couldn't find a whole lot of them. So one thing you might consider is, remember how I went to that Picoscope guided tests? There's some good information in there. You know, so let's see, when we get a little bit more time, let's look in the IN and see if we can find a sample waveform. But it seems like they gutted a lot of it out of there. It's in the old manual. They didn't gut the paper version, but the online one, they're like, you know what, this is